A lot of our work in Chapter 11 is going to be centered around determining whether or not a series converges or diverges. One really helpful thing is something called the Nth Term Tests. Now, if a series converges, what that means is that its sum adds up to something finite. And if it's going to add up to something finite and you've got an infinite number of terms, at some point, those terms have to be getting really, really small so that their limit has to approach zero. And hopefully it does so fast enough that it can converge. Now, if the limit of these terms approaches zero, the Nth term test tells us absolutely nothing. And this is really hard for students because it's a non-starter. If you're trying to prove convergence, you can't use the Nth term test. The Nth term test is really good, though, for showing that a series diverges. As I said just a minute ago, in order for a series to converge, these terms eventually have to get close, really, really close to zero. And if they don't do that, if the limit here is something other than zero, the series diverges. So this is often an easy way to show that a series diverges. And let's do that with looking at this example. So let's see, we're on example H. I have to switch over to the Greek alphabet pretty soon. So the sum from n equals 1 to infinity of 6 over the square root of n minus 6 over the square root of n plus 1. Okay, so one of the things that we want to do is find an expression for the series of partial sums. So S sub n is the sum of the first n terms. And let's see if we can't find an expression for that sum. So to do that, let me start looking at a few of these partial sums. Now, S sub 1 is just going to be the first terms. S sub 2 would be the sum of the first two terms. So I'd have 6 over the square root of 1 minus 6 over the square root of 2 plus the next term would be n equal 2, so it'd be 6 over the square root of 2 minus 6 over the square root of 3. And what I want to point out to you is that without taking out my calculator, I can easily see that those two cancel. Okay. Let's look at one more and then see if we can't spot the pattern. S sub 3, 6 over the square root of 1 minus 6 over the square root of 2 plus 6 over the square root of 2 minus 6 over the square root of 3 plus 6 over the square root of 3 minus 6 over the square root of 4. Now, before you start cranking out your calculator, let's go through and see if we can't do some simplification. Kind of like the last one, those two disappear. But then these two disappear as well. And so what you're left with is 6 over square root of 1. Let's just call that 6 minus a square, or 6 over the square root of 4. And I know that simplifies, but I kind of want to leave it there. So what's this going to look like in general? Well, in general, all of these things kind of collapse on themselves. And in that sense, this is something called a telescoping series. Let me show you why it's called a telescoping series. It's kind of like an old pirate's telescope, where this thing would collapse on itself. So you can just smash it down to something small like that. And that's what's happening with our series, is that it's collapsing on itself. And all I get is these n terms. So now, When I do this, I'm going to get the first N term, which is a 6, and the last N term, I got to be a little careful of. So when I did S sub 2, I ended up with 6 over the square root of 3. When I did S sub 3, I ended up with 6 over the square root of 4. So what's S sub n going to look like? I have the 6 minus 6 over what?
N plus 1.
Square root of n plus 1. Perfect. Perfect. So this is one more than this. That's why I didn't want to simplify this as, just a 2. That's because it was important to see the relationship between n here and n here, n here and n here, and so on. So that's cool. So if I want the sum of the first 100 terms, so let's do the sum of the first 99 terms. S sub 99 would be 6 minus 6 over the square root of 100. Or it'd be 10, it'd be 0.6, it'd be 5.4, would be that sum. Yay. So now, you could be asked to identify a plot or find the sum. We'll find the sum in just a minute. But for now, let's actually graph two things. We're going to graph S sub n and A sub n. Now, A sub n is just going to be these terms, 6 over the square root of n minus 6 over the square root of n plus 1. So we're going to graph both of these. Both of these are going to be input into my calculator. This one will be first, this one will be second. My calculator is in sequential mode. That's why when you hit the y equals key, you don't get y equals like you're used to, you get this other funny stuff. Now this is not a recursive sequence, so I don't have to worry about u sub 1, u sub 2, v sub 1, v sub 2. But here's my sequences. I've got A sub n up top and S sub n down below. When you get those set, then we'll go adjust our window. We'll have to adjust our window maybe a couple times, but that's okay. So I would start by setting n min to 1 and max to 10. That way we get the first 10 terms. And then let our calculators do the rest. When I say let our calculators do the rest, what am I suggesting?
Zoom 0.
Zoom 0, yeah. All right. Let me get rid of that crazy line there. You can change the style of your graph by cursoring over to the left of your equation. Press enter, cursor down once, and then change things around. I just want it like that. So you got to go down to the bottom, press enter, then we can graph it. So, okay, cool. So what am I getting? Well, the blue is my list of terms. Where's my list of terms going?
Down.
Yeah, it's going down and down. In fact, the adjustment that I suggested we might want to make afterwards is let's go down, instead of y min is 0.00 or 0.088, let's just let y min equal 0, because that way we'll see the x-axis. And it's just much more comforting and more understandable if you have the x-axis there. So with that little change, can anyone tell me a number that these are getting close to?
0.
0, yeah. Now, in order for a series to converge, these numbers have to do just that. They have to get close to 0. Now up here, this is the sum of these terms. And the sum of those terms is kind of leveling off as well. But it's nice that you can see both of them on the same graph. So that's the plot here. And let's go back to our calculations here and see if we can't find S. Now S is just going to be the sum of my series. In fact, let me just put that up here. As a reminder, S is that whole sum. S is the limit as n approaches infinity of S sub n. But I know what S sub n is. S sub n is 6 over the square root of 6 minus 6 over the square root of n plus 1. What's that limit going to be? You don't need L'Hopital's rule for this one. What happens is to this term as n goes to infinity?
Goes to 0.
Goes to 0. So I end up with 6 minus 0, which is 6. In fact, if you went back to your graph, let's go up to our window, Y max. Let's do Y maxes. Let's do 6.5. Eventually, what you should see is that the graph would get closer and closer to 6.5. And let me make a couple other changes. I'll make n max maybe, we'll do it 13. And 15. Let's just see what it looks like now. Okay. What you see is that the sum is leveling off. The sequence of partial sums is getting closer and closer to this horizontal line, indicating that the sum is, leveling off. And that's because the individual terms we're adding are getting closer and closer to 0. So it's not, each one of these terms is not contributing much to that sum. That's why it's increasing so slowly.
You could also check with table.
Yes.
Don't
You can
put
also
in
check the table.
I put in 10,000 for my end and the crash my calculator.
That's too funny. Yeah, you can take a look at the table. That's not a bad idea as well. All right, so it doesn't like non-integer values when you have things set up this way. But, you can type in 2, 3, 4, 5. Let's get wild. How about if we type in 10, 20, 30, 100. There you go.
Don't do 10,000, it crashes.
10,000, it crashes? All right, so let me do 1,000 then. Boy, it's not liking this one. Something that I'm not especially fond about the TI in 84s is that they seem to be underpowered in terms of their computing processor power. The TI Inspires are much faster.
Yeah.
But, it's rare that we run into something like this. Look at that. So next to 0, getting closer to 6. Boy, it's certainly taking its sweet old time there, but it eventually does get to 6. We know that. We proved it. One last one for this section in terms of a telescoping series.
Could you go back to the limit thing real quick?
Yeah. Question here?
Yeah. So are you just? I'm kind of confused on what exactly is like A sub n versus S sub n. Is that
All
just
right.
like?
Appreciate that. That's A sub n. A sub n is just the individual terms. So A sub n is this general term. A sub 1 is just that. It's just plugging in 1 here into that series. A sub 2 would be this one right here, plugging in 2 in for that term. So that would give you something like this, and so on. But A sub n is just the general term that you're summing up, whereas S sub n is the sum of several of these terms. So in particular, the first n of these terms. Let me see here. So let's take a look at S sub 2. S sub 2 is A sub 1 plus A sub 2. It's the sum of the first two terms. S sub 3 is a sub 1 plus a sub 2 plus a sub 3, and so on. S sub 4 would be the sum of the first four terms. So is that helping you out, the distinction between A and S?
Yes.
Okay, good.
Yeah, I got it. I got it.
All right. So yeah, A sub n is just our general term here. Awesome. So one last one, another telescoping series example. And this one's going to be n equals 1 to infinity of 6 over n times n plus 3. Now, I'm not sure exactly what I would do on an exam in terms of telling you how to solve things, how to prove things, etc. You're going to have a whole bag of tricks by the time we're done with working with series. And it's going to be up to you to know if you're going to use the nth term test, if it's a geometric series, are you going to use some properties of a telescoping series. Now, with telescoping series, you're going to have something here that is going to have a denominator that's going to factor. So in this case, you can break this up using our tricks from partial fractions into, let's see, this would be 2 over n minus 2 over n plus 3. And that comes from our work with partial fractions. And if you're wondering how I got that, I had to figure that out ahead of time. But it's that stuff over here. 6 over n times n plus 3 equals a over n plus b over n plus 3. And when you solve that, that's when you get this up here. All right, let's take a look at things here. So to look at things there, we're going to do the same thing we did with the previous example, which is look at the sequence of partial sums. And let me maybe jump up a little bit. We'll start with S sub 3. Let's see, you want S sub 2 or S sub 3? Now we'll start with S sub 2 and then maybe do S sub 3. So S sub 2 is going to be the sum of the first two terms. So that'd be 2 over 2 minus 2 over 5 plus oh, no, that was wrong. I'm sorry. I screwed that up. That should be 2 over 1 because you're going to start up with a sub 1, plugging in a 1 here. 2 over 1, 1 plus 3 is going to be 4, minus 2 over 4. Now, if n equals 2, here we'll get a 2, here we'll get a 5, and nothing's canceling. Bummer. So let's take a look at another one, S sub 3. Well, that's going to be 2 over 1 minus 2 over 4 plus 2 over 2 minus 2 over 5. So A1, A2, A3 would be 2 over 3 minus 2 over 6. And now finally we're going to start to see some cancellation, I think. Where are we? No, we're not. No, we have to start looking at S sub 4. Let's see, 2 over 4 minus 2 over 7. Finally, we're starting to see some cancellation. Wow. But you have to go a long ways to see that cancellation. That 2 over 4 term here and that 2 over 4 term here cancel. Let's just write one more term here, make this S sub 5. I'm going to cheat. Let's put on the 5th term here. So A sub 5 will be 2 over 5 minus 2 over 8. Did I pick up any more cancellation with that term?
Yeah, the 2 over 5.
Yeah, the 2 over 5 term cancels. So the next term is going to cancel out the 2 over 6 term. I don't have any room to show that over here, but it will cancel out. And so eventually, you're going to have to figure out what S sub n is going to look like. Now, S sub n, for S sub n, you're going to be left with certain terms. Let's see if we can't spot those. That one's not going to cancel out, that one's not going to cancel out, and that one's not going to cancel out. So your first 3 terms of these parentheses, so it's going to be 2 plus 1 plus 2/3 minus. And now let's see what's not going to cancel out. On the back end of this, we're going to have terms like for S sub n.
How does the 2/6 cancel out?
That would be the next term here. So it's not canceling out of this one in particular, but would cancel out of the next term.
I see.
So if I did S sub 6, then I would have a 2 over 6 minus 2 over 9. So let's call that S sub 6 now. And that's where you get the cancellation of that one. And the reason I wanted to acknowledge that is because I want to see, well, what's going to be left. And of these terms, the first 3 terms aren't going to have anything that cancel with them. And then the last 3 terms in something like this, so for S sub 6, we have 7, 8, and 9. In general, we'll have 2 over n plus 1 minus 2 over n plus 2 minus 2 over n plus 3. The reason this one is harder is because there's a large gap between these 2 terms. You have to go 3 terms before you get from n to n plus 3. And that's why this one was a bit more of a pain than the previous one, which only had a gap of 1. All right, so this is 3 plus 2/3, call that 11/3. The sum of our expression then is going to be the limit of, our limit as n approaches infinity of S sub n, which is going to be the limit as n approaches infinity of 11/3 minus 2 over n plus 1 minus 2 over n plus 2 minus 2 over n plus 3. But there's good news in this. What happens to these terms in the limit? They all go to 0. So you can actually calculate the sum of this, and it would be 11/3. So with these, it's just a matter of figuring out which one of your beginning terms don't cancel. Personally, I learned that I need to start out with a little bit bigger number when the gap is bigger. There. Okay, all done with that one. In fact, all done with section 11.2. Anything on this to wrap up?
I'm kind of confused on where you got those last three terms from, like the 2n plus 1, the 2 over n plus 2. Where
Sure.
exactly is that?
It's a great question. So looking back here, and eventually I think I settled down at endpoint S sub 6, I looked at the things that didn't cancel out. Now the things that didn't cancel out were these three right here, which was your beginning terms. Those three, oops, there. And then the last three, right? Now, what you have to do is you have to take a look at the n that you have here and the numbers that you have here. So if I have a 6, then this is one more than the 6. So when this is an n instead of a 6, then that term should be n plus 1. It should be one more than this. Likewise over here, 8 is 2 more than 6. So that gives me 6 plus 2, all right, or in general, n plus 2. And last but not least, the 9 is 3 more than the 6. So the general term is n plus 3 there. Does that help out?
Yeah.
Okay. So all these other terms collapse on itself in that same fashion the last one did, because it's a telescoping series. All right, good question. Anything else I can help out with here? Okay, let's stop this one.